right, so today we're going on a quest. We're on the hunt for a statistical model that can help us peek into the future. But, this journey is filled with some tough choices and more than a few hidden dangers. So, where do we even begin? I mean, this is the million-dollar question, isn't it? Can we really look at a pile of data from the past and figure out what's going to happen next? You've got analysts everywhere, from Wall Street to Washington, betting fortunes on the idea that yes, they absolutely can. But how? Well, every hero needs a weapon, right? For our analyst, that weapon is multiple linear regression. It's this incredibly powerful technique that lets you stop looking at a problem through a tiny keyhole, and instead you get to see the whole picture, how a bunch of different factors are all working together to create an outcome. So what is this thing, really? Think of it like this. You want to explain one thing. We'll call that our dependent variable. Let's say it's the return on a group of bonds. Now, instead of just looking at one possible cause, we look at multiple things that might influence it, like interest rates or how risky the bonds seem. We're basically trying to find the secret recipe that connects them all. Okay, now every model is built from a blueprint, and yeah, it looks like this. But don't worry about all the symbols. Seriously, this is just a recipe. The Y is the thing we want to predict, the X's are our ingredients, all the different factors we're testing, and the most important part? Those are the B's, the coefficients. They're the measurements telling us exactly how much of each ingredient to add to the mix. Let's make this feel a little more real. Imagine we've got a model that's trying to predict bond returns. The coefficient for bond yields is negative 5.05. You know what that means? It means for every 1 unit jump in yields, we expect a 5.05% drop in returns if credit spreads stay the same. And that last part is so important. Each number tells you the unique impact of one ingredient, totally separate from the others. It's how we untangle these really complex relationships. Building a model is actually a lot like building a house. You can have the most brilliant, beautiful blueprint, but if your foundation is cracked, the whole thing is just not safe. For a regression model, that foundation is built on a handful of really crucial assumptions. And here they are. These are the 5 critical stress tests for our foundation. Is the relationship actually a straight line? Are the errors consistent? Are all the factors truly independent? If our model fails any one of these tests, the entire structure we've so carefully built could just come crashing down, and that could give us some dangerously wrong answers. Let's see one of those tests in action. Take a look at the image on the left, the one labeled homoscedasticity. See how the errors are spread out nice and consistently? That's a solid, stable foundation. Now, look at the right. That's heteroscedasticity. The errors are getting wilder, more unpredictable. That is a major crack in the foundation. It's telling us our model is unreliable and we just can't trust its predictions. And there's another huge structural flaw we have to watch out for. It's called multicollinearity. So sticking with our house metaphor, this is like trying to build a wall using 2 beams that are almost identical. They aren't providing separate, independent support. In a model, this is what happens when 2 or more of your key variables are super correlated with each other. I mean, it really just boils down to this simple question. If 2 of your variables are basically telling you the exact same thing, the model starts to get, confused. It has a really hard time figuring out which variable is actually doing the work, and that can make your results totally unstable and almost impossible to interpret. So, our analyst has a blueprint. They know what dangers to look out for. But with dozens of potential ingredients to choose from, how do they pick the right combination? How do they decide which model is truly the best one? Well, that requires a whole new set of tools for judging their own work. The first step is to just use a smarter measuring stick. A lot of people have heard of R-squared. It tells you how much of the outcome is explained by your model. But it's got a big flaw. It almost always goes up when you add a new variable, even if that variable is totally useless. That's where adjusted R-squared comes in. It's the smarter judge. It actually penalizes the model for adding extra complexity if it's not adding real explanatory power. But for the final showdown, analysts bring in the ultimate judges, AIC and BIC. Think of them as reading a model on 2 things: how well it explains the data and how simple it is. They love accuracy, but they hate unnecessary complexity. And in this competition, the lowest score wins. They're both hunting for the model that does the most work with the fewest parts. And this table right here shows the judges' scores. Watch what happens. As we start adding more factors, the adjusted R-squared goes up. You'd think that's good, right? But now look over at the AIC and BIC columns.
The BIC, who's our strictest judge, gives its lowest score, the winning score, highlighted here, to the simplest model with just one factor. It's basically telling us, hey, adding all that extra stuff didn't actually make the model fundamentally better.
So here it is, the big reveal of our whole quest. The perfect model? It doesn't exist. It's a total myth. The real work of an analyst isn't some straight line to a single perfect answer. It's a cycle, over and over again. You build something, you test it, you learn from it, and then you go back and build it again, always trying to make it just a little bit better. And here's a final piece of wisdom from our source material that really turns what you think you know on its head. A high R-squared isn't the goal. A bad model can actually have a really high R-squared if it's overfit, which means it's basically memorized the random noise in your data instead of finding the true pattern. A good, useful model might have a lower R-squared, but be way more reliable for actually predicting the future. Which brings us to our final big question. If every single model is flawed, just an imperfect reflection of reality, and if the quest for perfection is a myth, how do we decide when a model is good enough to actually trust with a real-world decision? That right there is the true art and science of doing this kind of work.